Right, let's talk about transformers. They are, without a doubt, the silent, unassuming workhorses of our entire electrical grid. But like any workhorse, they have their limits. So today, we're going to explore what happens when you push a transformer right to its absolute magnetic breaking point. It gets pretty interesting.
So, what exactly is this breaking point? Well, it's not a physical snap or some kind of explosion. It's something far more subtle and in many ways more dangerous. It's a fundamental limit within the transformer's magnetic core. And once you cross it, believe me, everything about how that transformer behaves is about to change, and not for the better.
Okay, so before we dive into how things go wrong, we really need to understand the rules the transformer is supposed to be playing by. Let's take a look at how a transformer's magnetic core works under normal, everyday, happy conditions. Here it is, the key definition: transformer saturation. Think of the magnetic core like a sponge. Under normal conditions, it soaks up magnetic flux beautifully and efficiently. But there comes a point where that sponge is just completely, utterly soaked. It literally cannot absorb one more drop. At that point, it stops being this elegant power transfer device and becomes, well, something else entirely.
Now, this is the transformer's rulebook, the BH curve. It's pretty straightforward. Along the bottom, you've got H, which is the magnetizing force we're putting in. And going up the side is B, the magnetic flux density we're getting out. See that lovely straight line at the beginning? That's the sweet spot. That's the linear region where more force in gets you more flux out. It's exactly where a transformer is designed to live its life.
But look what happens as you push it further. The curve starts to bend and then just flattens out. That bend is called the knee of the curve, and it perfectly illustrates the breaking point. Just as the quote says, you can keep piling on more and more magnetizing force, but you get almost nothing extra in return. The core is saturated, it's maxed out, game over for efficient operation.
Of course, transformers are designed to stay well clear of that knee. So what on earth could possibly push one over the line? How does a perfectly good, well-behaved transformer end up in this dangerous, saturated state?
Well, it usually comes down to one of three main culprits. First, you've got overexcitation. That's basically when the voltage is too high for the operating frequency, which just shoves way too much flux into the core. Second is a DC bias. This is a sneaky one where a rogue direct current gets in, shifting the whole operation, pushing one half of the AC cycle deep into saturation. And third, you have abnormal transients. Think of the massive surge of current when you first switch a transformer on. It's a momentary shock, but it can cause a colossal flux spike.
So once that line is crossed, the backlash is immediate, and it is severe. In an instant, the transformer's electrical personality completely changes, and it stops behaving like a transformer at all. Let's have a look at how this backlash actually builds up. And this just shows you the stark contrast. Normally, the core provides high inductance, which acts like a big, strong dam, holding back the current, keeping it small and controlled. But when you hit saturation, the core's ability to support that magnetic field just evaporates. The inductance collapses, the dam breaks, and the magnetizing current, which was a tiny trickle before, suddenly skyrockets into a flood, completely distorting that clean, beautiful sine wave we need for our power.
And this distortion creates what engineers call a harmonic mess. That current waveform becomes all peaky and spiky, and it's suddenly full of these unwanted garbage frequencies, the odd harmonics. The transformer just loses all its good transformer behavior. And this is critically dangerous for the little instrument transformers, the CTs and VTs, that our grid protection systems rely on. If they saturate, they can't measure a fault correctly, which might mean a circuit breaker doesn't trip when it absolutely needs to.
Now, this electrical chaos doesn't just stay on a graph or in a circuit diagram. Oh no. It translates directly into real, physical stress on the transformer itself. We're talking serious heat, loud noises, and immense mechanical forces.
And that's the key point, isn't it? The abstract electrical problems we've just been talking about, that skyrocketing current and distorted flux, are about to show up as very real, very tangible, and potentially destructive physical effects.
This table really shows you the chain reaction. That massive spike in current causes a huge increase in what we call I²R losses. That's just a fancy way of saying the copper windings get incredibly hot, creating dangerous hotspots that rapidly cook and age the insulation. At the same time, that chaotic nonlinear flux causes the core itself to heat up and physically vibrate, creating a loud, ominous hum and putting the whole structure under mechanical stress.
You know, a problem in one transformer is bad enough, but these things aren't islands. They are vital nodes in a massive interconnected grid. And when a big transformer saturates, you better believe the entire system is going to feel it.
This is where the consequences really start to scale.
Those nasty current harmonics we mentioned, they don't just stay put. They get injected back into the grid, basically polluting the power quality for everyone connected to it. And to hammer the point home, if a current transformer saturates during a major system fault, the protective relays get bad information. They might fail to trip the breaker, and that's how a simple, containable fault can cascade into a widespread blackout.
So given how truly awful the consequences are, it's no surprise that the entire field of power engineering is built around one simple goal: keep transformers out of saturation. This isn't about cleaning up a mess. It's all about prevention through clever design and smart operation.
And it really boils down to these 4 pillars. First, you have to strictly respect the voltage to frequency or V per hertz limits during operation. No exceptions. Second, it's about designing the transformer right from day one, choosing the right core material and sizing it with a healthy safety margin. Third, you have to actively manage things like DC bias and those big inrush currents. And finally, you monitor its health constantly, looking at things like temperature and dissolved gas in the oil to catch any signs of stress long before they become a problem.
Honestly, I think this quote from our source material just sums it all up perfectly. Saturation is that precise moment when a highly sophisticated piece of engineering gives up and it just reverts to being an overloaded, inefficient, and very, very hot lump of iron and copper. The goal is to simply never let it get there.
And that really leaves us with a final thought, doesn't it? As our grids get more and more complex, with renewable energy sources and new kinds of loads popping up everywhere, the challenge for engineers just gets bigger. How do we ensure these foundational workhorses are designed, protected, and operated so that they never, ever reach that magnetic breaking point? It's a fascinating challenge. Thanks for joining me.